here. And oops, no, okay. Yes, so the port Hamiltonian descriptor system you can say here, so you can see here. Most important for us are the matrices E, Q, J, and R, which are then the underlying pencil we are interested in. And an important feature is that you look at the Hamiltonian, which is given like this and describes the distribution of internal energy about energy storage elements. And so therefore, it is natural to assume that this is non-negative, which corresponds to a non-negative energy. So you end up with a pencil like this, and J is skew symmetric or skew Hermitian in the complex case. R is Hermitian positive semi-definite, and EQ satisfy the relation given here. In many applications, actually, the Q is just equal to the identity, and then the pencil simplifies, or the system simplifies to this structure here. So then both E and R are positive semi-definite, and J is skew symmetric. Okay, so here one example from applications. So there are numerous applications where these port Hamiltonian systems occur. So for example, in circuits, this is the case. And I don't want to go through the details here, just to show to you that this is really common in applications, and that actually we can have this matrices really not positive definite, but positive semi-definite. So here you have a zero. And so here you see that we have a skew symmetric part, but also a positive semi-definite. Actually, it is a minus R, but the R is positive semi-definite. Okay. And what can we say about these systems? So for this, I would like to briefly remind you about the Kronecker canonical form. So clearly, every pencil is equivalent to a Kronecker canonical form. When I say equivalent here, I mean strictly equivalent, but I will just briefly say equivalent. So we can have Jordan blocks associated with this finite eigenvalues. Then the sizes of the Jordan blocks we call the partial multiplicities. Then we have this n blocks. These are the blocks associated with the eigenvalue infinity. And the largest index that we have here is then called the index of the pencil. And in the singular case, we may have these rectangular Kronecker blocks. So we may have right singular blocks, and they correspond to the, so the size is then called the right minimal index. And here it is allowed that this index is 0, then this would correspond to a 0 times 1 matrix in this case. And this just means that to the pencil, one adds a 0 column. And same for the left indices. And also here we may have indices which are 0, and this corresponds then to adding a 0 row. Or if the minimal indices are larger, then we have blocks like this. So in that case, we can say the following about the spectral properties of these dissipative Hamiltonian pencils. Let's start for the case that our Q is the identity. Then actually one can say that a given arbitrary matrix pencil is equivalent to a pencil of this form, where E and R are positive semi-definite and J is skew Hermitian, if and only if these conditions here are satisfied. So the spectrum is contained in the closed left half plane, and with spectrum I always mean the eigenvalues that are in the Kronecker canonical form. So the eigenvalue is not, so even in the singular case, eigenvalue means then that we have a Jordan block in the Kronecker canonical form. So those are always in the closed left half plane. The ones on the imaginary axis are semi-simple if they are finite. So the eigenvalue infinity plays an exceptional role. So here the blocks can have size 2, which means is that the index of the pencil can be 2, and but not larger. And interestingly, all minimal indices are 0. So And this means, as I just explained, since this corresponds to adding 0 rows or 0 columns, that such a dissipative Hamiltonian pencil is singular if and only if the two matrices E and J minus R have a common kernel. And in fact, since you have even more structure, so the J and the R positive semi-definite, it turns out that this is even equivalent that all 3 matrices E, J, and R have a common kernel. So the last item is easily seen from here. So if we have something in the kernel here, then if you just multiply X star from the left, then you see this here is purely imaginary and this is real. So both must be real. And since this is positive semi-definite, we find that Rx is 0. But then from this equation, also Jx is 0. And so all 3 matrices then have a common kernel, which is a nice and interesting feature. So this was the version if we do not have the Q, or the Q is the identity. So what happens if Q is not the identity? So then recall, then E itself need not be positive semi-definite, but this product, Q star times E, is still positive semi-definite. Then we have the following result, and we have to add here that the pencil that consists of this E and Q should be regular, because otherwise actually one cannot say very much things. So then the pencil can be does not have any nice spectral properties in general. But if you assume this, then again one can show that this is equivalent to the following conditions, where are listed here in red the differences to the case with Q is equal to the identity. So still the spectrum is contained in the closed left half plane, and the finite now non-zero eigenvalues that are on the imaginary axis are still semi-simple. And now the partial multiplicity of the eigenvalue zeros can actually be 2. And still the index can be 2 that we had before. And now we have also a difference in the left and right minimal indices. So if there are left minimal indices, then those still must be 0. But if we have right minimal indices, they can actually be also 1. And this has an important consequence. We will come back to this in a few minutes. Okay, so we see we lose a little bit, but still these pencils are almost stable. So of course, the index can be 2 and the eigenvalue 0 is on the imaginary axis and need not be semi-simple, but all other eigenvalues are absolutely fine. Okay, now let's look at second order systems and see if we can find some structure that leads to similar properties. And indeed, this is the case. So if we consider second order systems, like here, a mechanical system where all the coefficient matrices are positive semi-definite, which means we have the underlying quadratic matrix polynomial given here. Then, interestingly, such systems have a dissipative Hamiltonian linearization, which looks like this. So here we have it in the form E minus J minus R and Q. And Q is not the identity in general, unless K is the identity. But if you look closely here, then indeed, if you multiply Q star and E, then you get a positive semi-definite matrix. And the remaining thing over here, J minus R, so the skew symmetric part is here, and the Hermitian part is indeed also positive semi-definite. Which means, that's nice, such a matrix polynomial, again, has this nice properties that the spectrum is contained in the left half plane. Can we get rid of the Q here? So can we also find a dissipative Hamiltonian linearization where Q is the identity? Fortunately, the answer is no, and I'll give you 2 reasons why this is not possible. One comes, well, of course, this is possible for, with linearization, I mean a template that works for all matrices. If I go back here, it works for all matrices MDK simultaneously. So of course, for some matrix polynomials, this may be possible, but in general, this is not possible to have such a template that works for all MDK and does not have a Q for two reasons. Because we have seen that there were these minimal indices restrictions. So if we have a pencil like this that we are aiming for, then the left and right minimal indices must be 0. And with the Q, we have it different, that the right minimal indices can be also 1. And this is important that this is allowed here, because if you would have such a linearization template for a general polynomial, then it turns out that the minimal indices cannot will not be exactly the same of the polynomial if you have, of course, a linearization that reflects the structure. So that's what I'm assuming here. But then the minimal indices, at least the left or the right minimal indices, have to increase by some numbers. And by the way, so this is a number, as you can see here, in total, the minimal indices have to increase by degree -1. And if we have degree 2, this means that the minimal that at either the left or right minimal indices has to go up to 1. And from this, we immediately learn that it's not possible to have a linearization like this, but you need one with a Q. And you also find out that the quadratic matrix polynomials must have all their minimal indices equal to 0, because only in this case then you can have right minimal indices which are exactly 1 here in that case, because going to the linearization, the right minimal indices have to increase because the left minimal indices are not allowed to if I want to use such a linearization. So this is quite a restriction. Okay, but still with this one can, right, I wanted to give a second reason. So as we have seen here, for this linearization, the eigenvalue 0 is semi-simple. And here we see that we have partial multiplicities, may have partial multiplicities of size 2. And now if we consider a matrix polynomial, then the index can actually be 2. This is easy to construct examples. And then if I look at the reversal, then the linearization template should also work for that. And but then I have partial multiplicities 2 at 0. So to guarantee that this is possible, again, we would have to use such a linearization. So that's the second reason that we have here. But still, even this pencil here has nice spectral properties. And I forgot that I even wanted to tell you more. So we can even be a little bit more general, and we can take a matrix polynomial where we add a skew-symmetric part to one of the coefficient matrices. So here I have done this for the middle term, and then it's still possible to obtain a dissipative Hamiltonian linearization. So the G, which is skew-symmetric, can just be put here in the skew-symmetric parts. And there are also other variants. If you put it in M or in K, this also works. So from this point of view, we can even have more general matrix polynomials. And for all those, we now can prove the results via the linearization. So all the eigenvalues must be in the left half plane. The finite non-zero eigenvalues on the imaginary axis are semi-simple. The index is as most 2. Eigenvalue 0 may have Jordan blocks of size 2, and the minima indices must all be 0. And again, this has the effect that the matrix polynomial is singular if and only if the 3 coefficient matrices have a common kernel. And using the same argument that I showed before, actually, this turns out that the 4 matrices have a common kernel. And this is a nice feature because this gives you the possibility to compute the distance to singularity easily, because you just have to check what is the distance to a common kernel of several matrices. And we did this in another paper. I'm not going to talk about this here, but just to mention that this is a nice application, that you have the that singularity is equal to a common kernel. This gives you a possibility actually to compute the distance to singularity. In general, this is a very hard problem. Okay, Now let's see if we can go to higher degree polynomials. And here I will not consider the case that we have somewhere also a skew-symmetric part, but let's look at matrix polynomials with positive semi-definite coefficients. And then the question is, if k is at least 3, can we still find a dissipative Hamiltonian linearization? And is this relevant actually? Do they somehow appear in applications? Yes, they do. Let me show here one. So, for example, the control problem for the Moore-Gibson-Thompson equation, it's a problem in nonlinear acoustics. This leads to a third order matrix polynomial, which has the following form. So A3 is the identity. Here we have a scalar multiple of the identity. And here we have triangular matrices, which look like this. And so one has to investigate this matrix polynomial. So, for example, to check is the stable, are all the eigenvalues in the left half plane. And this can then be used to select dominant poles for model truncation and model order reduction. So it would be nice if we could find a dissipative Hamiltonian linearization. So this was our question. And again, we have this nice feature that the polynomial is singular if and only if all matrices that we have here have a common kernel. So this can easily be seen actually, because if the matrix polynomial is singular, then in particular there exists a vector such that p of 1 times x equals 0. And multiplying then x from the left, we end up with this equation. And since all of these terms here, since all of them are positive semi-definite, all of them are non-negative, and thus getting 0 is just possible if all are 0. And from the positive semi-definiteness, we find that all these matrix vector products must be 0. So x is then actually in the common kernel of all matrices. So again, for those polynomials, one can easily detect the distance to singularity. And again, so we have this, that all left and right minimal indices of the polynomial are 0. That's good from this one point that I said, but it's also bad from another point. But this means that we cannot actually get a dissipative Hamiltonian linearization, because we call this shifting of the minimal indices if you go to the linearization. And the dissipative Hamiltonian pencils can only have right minimal indices that are at most 1. This means that with degree 2, there is already the end. And if we have degree 3 or higher, then this is not possible, because either the left minimal indices would have to increase or the right minimal indices would have to be at least 2, which is not possible for the linearization. So no chance here to get this dissipative Hamiltonian pencils. And even worse, so these polynomials may actually have spectrum in the right half plane. Here's a very easy example. If you take the scalar lambda to the third and plus 1, then this is has the eigenvalues or the roots that are given here, and this is in the right half plane. So there is no dissipative Hamiltonian linearization template, neither with or without Q. So we have to do something else. And at this time, let's become posH and look at posH pencils. So posH refers to positive semi-definite Hermitian parts, which means that we look at now at pencils that have the form given here. So we have an arbitrary skew-symmetric part, but the Hermitian part, but the Hermitian part should be positive semi-definite. So this is a generalization of these dissipative Hamiltonian pencils for the case that Q is the identity, because if we look at this pencil that we had earlier here, then we easily find that this is exactly the structure if we set J1 to equal to 0. And yeah, why do we consider those? Because we can those use as linearizations for our matrix polynomials with positive semi-definite coefficients. So here's an example for a linearization. And for this special linearization to be a linearization, we need that both A0 and A3 are positive definite, because even then, in the regular case, if A3 would be singular, then you would get a singular pencil here. So this only works if we assume that these two matrices are positive definite. And in the following, I will now in general use blue for the Hermitian positive semi-definite part and red for the skew Hermitian part. So indeed, you can see by these assumptions we have that the Hermitian parts here are positive semi-definite. This is a little bit unfortunate with this assumption on A0 and A3, but there are other linearizations where you do not need this assumption. And actually, you can have this for any odd degree that you can imagine. So I gave here examples for k equals 3 and k equals 5. So they look like this, and you have the identity matrices here, and the blocks always on the diagonal, which guarantee then that the Hermitian parts that you can see in blue are always positive semi-definite. This works nicely like this only for the odd case. For the even case, one has to assume that either one of the matrices AK or A0 is positive definite, because you can only realize it with some inverse here. But still, if you assume this, then you also get linearization templates that leads to a so-called posH pencil for matrix polynomials of even degree. Okay. These are not the other applications for posH pencils. So, for example, if we come back to our quadratic matrix polynomial, and if we now not only in one matrix add a skew Hermitian part, but also in another matrix like here, then the eigenvalues can actually be in the right half plane. And so you cannot any longer find in general a dissipative Hamiltonian linearization, but still you can have a posH linearization, which is, so the example is given here. So, and some of you who listened to Volker giving a talk on the break squeal problem, then this is actually exactly a matrix polynomial that appears in this application. So, so that's also something that we have under control with these posH pencils. So now let's see what can we say about posH pencils, and are they sometimes equivalent to DH pencils? Then we have to know something about the eigenvalues, of course. So first, the general observation: the pencil may have actually an arbitrary spectrum in the right half plane. So here is an example constructed taking B non-negative, then you find the you get the eigenvalues alpha plus minus I times beta, which you can choose to be everywhere in the complex plane. So from this point of view, it seems that they are quite general, but we will see still we can say something. And also a nice feature that we had for the dissipative Hamiltonian pencils was that the index could only be 2. The index may in fact now be larger. So here is an example for index 3. You see the red is the skew symmetric part, and the Hermitian part is again positive semi-definite, but we have higher index here. So what can we say about the spectral properties now in general about these posH pencils? And there is an interesting connection between the posH pencil and the underlying skew Hermitian pencil just formed by the two J matrices. So it seems the R matrices are nice, so the bad guy is this underlying pencil here. So the first result that we could show is we may have actually now singular chains or minimal indices that are larger than 0. They can be, in theory, of arbitrarily large size, but then you have a corresponding singular chain. And the interesting thing is the vectors from this chain must be in the kernel of the two R matrices. And then this means that this is also a singular chain of the pencil that only consists of the two J matrices. And again, so what is the idea, how to prove that? The idea is just to make, so you will end up with equations like this. And from those you can conclude, due to the positive semi-definiteness, that the vector must be in the kernel of R. So that's basically what behind it. But the nice thing is that, so that now minimal indices of the full pencil are restricted by the minimal indices of the pencil just consisting of J. So if you have that pencil under control, then also the pencil P is automatically under control. Is this only for the minimal indices, or can we also say something, for example, for the index, for the eigenvalue infinity? Yes, it's a little bit more complicated here. So what it turns out that if the index of the underlying skew Hermitian pencil is at most k, or the minimal indices are at most k minus 1, then the index of the pencil is restricted to be at most 2 times k. But this number kappa, kappa here may actually double. And here are 2 examples. So here we have index 3. And if you look at the underlying skew Hermitian pencil, which is the red pencil, so just ignore now the blue one, then you see that you have here a singular block of size 1 times 2, and which corresponds here to the case that kappa is 1. Okay, I see. I have a slight. I have an error here in the kappa, but never mind. And again, if I consider this pencil here, which has index 4, you see if you ignore the blue one, then actually you have 2 blocks associated with the eigenvalue infinity of the underlying skew Hermitian pencil associated with the eigenvalue infinity of size 2. And so really the index doubles. So here we have the red pencil has index 2, but the full pencil has index 4. Okay. And even more can be said, for example, about the about positive eigenvalues. We already know that we may have singular minimal indices that are larger than 0. So singularity is no longer equivalent that all 4 matrices have a common kernel. But still, what you have is pencil is singular, then in both of the triples J1, R1, R2, and J2, R1, R2, the matrices must have a common kernel. But these 2 triples may have, of course, different common kernels. And if one of these, if you take 2 of these matrices and you see that they are form a regular pencil, then this immediately implies that the pencil itself is regular. And interestingly, if this is regular, then we cannot have eigenvalues on the real positive axis. And in the other cases, it's again this pencil that makes it difficult, or that causes the problems. So if we have a real positive eigenvalue, then this is also an eigenvalue of this pencil, or the pencil may also be singular. Okay, so we see that everything goes back to this underlying skew Hermitian pencil. And the question is now, can we even say more? So for example, if this underlying skew Hermitian pencil has all eigenvalues in the left half plane, is then the same true for the posH pencil? We were hoping for this a little bit until we found a counterexample, which I give here. So this is the underlying skew Hermitian pencil, and since we have written this with a plus here, actually this pencil has the eigenvalue minus 0.1. And so all here again, the same block So the eigenvalue is with algebraic multiplicity 4, and it is in the left half plane. Everything is fine. And then we add here a scalar multiple of these two semi-definite matrices. And then we plot the eigenvalue curves for different values of t when t ranges from 0 to 3. So the star marks when we have this eigenvalue with algebraic multiplicity 4 at minus 0.1. And you can see there are some values for t when it goes to the right half plane. And if you take r large enough, then everything is in the left half plane. But so unfortunately, this we cannot say. And thus the question arises, when actually can we guarantee that all the eigenvalues are in the left half plane? And for this, as a tool, we use the numerical range. We heard about that in the previous two Ocelot talks. And so the numerical range of a pencil is defined as the set of all complex numbers. Oh, this should be a mu here, I see, that x star L of mu times x is 0 for some non-zero vector. And then clearly this contains the spectrum. And so if we can localize the numerical range in the left half plane, then also the spectrum will be there. One has to be a little bit careful here, because it may happen that this numerical range is the full complex plane. This happens if there are common isotropic vectors. Common isotropic vector means that this here is satisfied. So then in that case, one cannot say much. So the numerical range does not give much information. And so what one can show is if the two R matrices do not have a common kernel, then actually it is guaranteed that the numerical range is not the full complex plane. And in fact, then you do not have common isotropic vectors. And in that case, of course, also L is regular. And yeah, but not all of these implications can be seen in the other direction. Okay, and one result, so this is now a little bit technical, how we can localize the spectrum is the following. So if you take a linear combination of these matrices R1, R2, and then also at beta times, and then one of the matrices here. Here we chose J1. And you look at the supremum, such this is still positive definite matrix. So this makes sense if the kernel of R1 and R2 is if they do not have a common kernel, because then this matrix here is positive definite. And so for some values of beta, you will actually have here that this is still positive definite. And then you can conclude that the numerical range must be disjoint from the set that is given here. So what you see here is just the following. So here you can just, the angle must be less than this particular value, and this corresponds to a stripe, and both together then looks like this. So this is here now the region that is excluded. So here we have this part that gives the angle, which came from the arcus tangens, and the other part comes from the stripe you have here. And so here this is shown for, so we had a parameter t, this was chosen for t equals to 1. And thus you have in the numerical range such a Pacman-like structure usually. And but you can see it's in the right half plane. By the way, the picture was generated by choosing random points to compute the numerical range. Okay, still, when is the spectrum contained in the left half plane? We have several conditions. Let me just name one. So, for example, if you can show that this expression here is not positive for all vectors x, and if L does not have a common isotropic vector, then the numerical range is contained in the left half plane. And this is, of course, not that easy to check, but you can easily give a stronger condition that implies this. And this is, for example, here, if you look at the Kronecker product of the J matrices and subtract the Kronecker product of the R matrices, and this is a negative semi-definite matrix, then this is satisfied. So this basically shows that if the R matrices dominate the J matrices, then the spectrum is in the left half plane. Now let's get back to the matrix polynomials with positive semi-definite coefficients. And can we now use the results that I presented you earlier to say something about this? And yes, because we had this posH linearizations. And remember that the underlying skew Hermitian pencil was saying a lot about minimal indices and index and so. And if you look at this here, then you find that this pencil does not have any eigenvalues, but only left and right minimal indices of a fixed size. And this gives restrictions on the index, for example. So you find out that the index of such a matrix polynomial cannot be larger than the degree of the matrix polynomial, which fits nicely to the theory that we had for the quadratic case. We may have index 2, but for a cubic case, we may have index 3, but not higher, and so on. And we can also say something concerning the eigenvalues. So here, if the polynomial is regular, then the numerical range must be contained in this region here, which is depicted here. So for k equals 2, it is the left half plane. But for k equals 3, you may have eigenvalues in the right half plane, but only in this additional part that is here marked in red. And then the angle gets closer and closer to the real line, the higher the degree is. Why is this the case? This is actually quite easy. This goes back to a result by Cowling and Tron on the zeros of scalar polynomials, because numerical range, if you look at this, then you just get polynomial, scalar polynomial here with non-negative coefficients, and it is known that the zeros then must be in this region. And actually the bound is sharp. Bound is sharp. So if you look at this polynomial, then you indeed have roots exactly on these lines that are given here. Okay. Yes, and the end, let's come back to this special cubic matrix polynomial that we had from the application. So in that case, we can give an easy condition when the numerical range is in the complex plane. So here the this condition must be satisfied. And for our particular application, this is easy to check because the matrices that you have to compare have a very similar structure. So this then just reduces to that the parameter alpha you have here, if this is larger than 1, and if the parameter beta is larger than or equal to gamma, then it is guaranteed that the numerical range, if thus all eigenvalues are in the left half plane. Okay, so that's what we can say, and I hope that I convinced you that actually dissipative Hamiltonian pencils are pretty cool or nice, and posH pencils may be considered a little bit posH, but we have seen they have still some cool properties, and dissipative Hamiltonian pencils, all eigenvalues are in the left complex plane. But for the posH pencils, if we have the skew Hermitian pencil somehow under control, then we can say something about the full pencil as well. And so here are references. And with that, I would like to thank you for your attention.